In this lecture, we are going to discuss about path function and point function, and then about introduction to heat transfer. The outline of the presentation is like this. Let us start with the different forms of differential functions such as point function and path function. Then we will go to the introduction to heat transfer, and finally we will discuss about Zeroth Law of Thermodynamics. There are basically two different types of differential functions available. One we call it as a point function, and the other one we call it as a path function, which is nothing but other name for these two differential functions are called as exact differential or inexact differential, and this exact differential is also called as perfect differential, and the inexact differential is also called as imperfect differential. So this exact differential is what we refer it as point function, and the inexact differential is what we call it as path function. And whatever you have studied in the differential equations from your schooling, right, there we used to write D for differentiation. So that refers to the exact differential or perfect differential. There exists one more differential function called imperfect differential or inexact differential, that is represented by D cross, or we will write delta. So throughout this course we are going to use delta to represent the inexact differential, and if the differential is going to be exact differential, then we will use the notation D. The exact differential is what we call it as the point function, and the inexact differential is what we call it as the path function. So let us discuss about these point function and path function in detail. Now let us come to the point function. Right? Point function is nothing but exact differential or perfect differential, and all thermodynamic properties are exact differential, right, are point functions. Let me explain this. Let us consider a system which is at state 1, whose pressure is P1 and volume is V1. Now assume that this undergoes a process, right? From state 1 it undergoes a change of state, or it undergoes a process, and after undergoing the process it comes to state 2, and assume that it is going to follow path A. The path followed by the system during this change of state or during this process is, let us say, it is path A. At state 2 the properties are P2 and V2. The path followed by the system during the change of state or during the process from change of state 1 to 2 is path A. Assume that there exists one more path, path B, by which also the system can reach state 2 from state 1. So there are two paths, path A and path B. The system can undergo either path A. When it undergoes a process from state 1 to state 2, it can either follow path A or path B. So now for this case, let us say I want to determine the difference in pressure or difference in volume along path A and path B. Now you consider along path A. Along path A, the change in volume or the difference in volume is V2 minus V1. Correct? And along path B, the change in volume is also again V2 minus V1. So we will get the same value irrespective of the path followed by the system. Whether the system can follow path A or path B, irrespective of the path followed by the system, the change in volume is going to be V2 minus V1. That means we are going to consider only the end state, the property at state 2 and property at state 1. Similarly, if you want to determine the difference in pressure, irrespective of the path followed, along path A it is P2 minus P1, along path B also it is P2 minus P1. So from this what do we infer? If you want to determine a change of property, let us say it can be volume or it can be pressure, then the change in property is given as it depends only upon the end state, and it does not depend upon the path followed by the system. Such differential functions we call it as point function. So all thermodynamic properties, they does not depend upon the path followed by the system, whereas it depends only upon the end states. So they are called as point functions. Now let me explain about what is a path function, then it will be very clear. Right? For that, let us consider a system and it undergoes a change of state. Now you consider a system which is at state 1. Its initial state is state 1 and the corresponding pressure is P1 and corresponding volume is V1. Now this system at state 1, it is going to undergo a process, and after undergoing a process it reaches state 2 where the pressure is P2 and volume is V2. To reach state 2 from state 1 for the system, there are three paths available: path A, path B and path C. So system can reach state 2 from state 1 along path A, or along path B, or along path C. So there are three paths available. Now assume that I want to determine the work transfer during this change of state. So if it is going to follow path A, then the area under the curve along path A is going to be this, right? So the area under the curve along path A is this area. If it is area under the curve along path B, then area is different. The area under the curve along path C, that is going to be still higher and it is different. Okay. So the area under the curve in a PV diagram represents the work transfer. If the system is going to follow along path A and the work transfer is going to be small. If the system is going to undergo a change of state from 1 to 2 along path B, then the work transfer is going to be more because the area under the curve in the PV diagram is higher. Now let us say in the case of path C, still higher area under the curve we are going to get, therefore the work transfer during the process 1 to 2 along path C is going to be more, right? So the work transfer depending upon the path followed by the system. It does not depend upon the end states alone. Right? So it depends upon the end states and also the path followed by the system. So therefore, this work transfer, we say that it does not depend upon end state and it depends upon both end state and the path followed by the system. So this such type of function we call it as path function because it depends upon the path followed by the system. Okay, so now I think like you are very clear about what is the difference between point function and path function. Point function means it depends only upon the end states of the system, right? When the system undergoes a process, then change in property, thermodynamic property, that depends only upon the end state and it does not depend upon the path followed by the system. Whereas, for example, if it is a work transfer and when the system undergoes a change of state or when a system undergoes a process, then the work transfer depends upon the path followed by the system and also the end states. So such functions we call it as path function. Okay. Now this is an inexact differential and it depends upon the path followed by the system. So we cannot say that work is a thermodynamic property or it is not a state function or it is not a point function, right? So since we have two differential functions, in order to differentiate these two differential functions, we are going to use two notations, right? For perfect differential or exact differential, we are using the notation D, and for inexact or imperfect differential, we are going to use the notation delta. Some authors they use D cross, right? So if it is the work transfer, then it is integral 1 to 2 del W. That should not be written as W2 minus W1. In the case of change in volume, we write V2 minus V1, final state, final volume minus initial volume. That cannot be written here. Here instead we will write like W1 to 2, right? If you want to determine the work transfer during the process 1 to 2, then it is given as W1 to 2. So now let us say a system is undergoing a cycle. What is cycle? Cycle is nothing but a series of processes in such a way that the initial state and final state of the system is going to be the same. So for a system undergoing a cycle, then if you want to determine the change in any thermodynamic property, because your initial and final states are same, then for that cycle the change in the thermodynamic property is going to be 0. So therefore we say that in a cyclic process the cyclic integral of a thermodynamic property is 0. So for any thermodynamic property, if the system is going to undergo a cycle, then the change in thermodynamic property is going to be 0. It can be volume, it can be pressure, it can be temperature. Whereas in the case of transfer, when a system undergoes a process and there exists work transfer, then the differential work is given as del W equal to P into dV. Assume that it is going to be a displacement work. Okay, so now from this I can write dV equal to 1 by P into dW. So this volume, change in volume is an exact differential. So this exact differential is equal to product of this integrating factor 1 by P and the inexact differential work transfer, right? So del W is the inexact differential, 1 by P is an integrating factor, and that will give you an exact differential. So exact differential equal to product of this factor into inexact differential. Now coming to the introduction to heat transfer, right? What is heat transfer? Heat is nothing but a form of energy. So this energy transfer by virtue of temperature difference is what we call it as a heat transfer. By nature, heat transfer occurs from higher temperature to lower temperature. Wherever you have difference in temperature, then there will be definitely heat transfer phenomenon will be there. And the various modes of heat transfers are conduction, radiation and convection. So similar to work transfer, heat transfer also we say that this is an energy in transit. So always this transfer will be there. So heat transfer is a form of energy in transit, and this is felt only at the boundary. So therefore this is also called as a boundary phenomenon. And this heat transfer is also a path function similar to work transfer. So this is not a thermodynamic property. So similar to work transfer, heat transfer is also a path function. That means it depends upon the path followed by the system as well as the end states when a system undergoes a change of state or a process. Now let us see the difference between work transfer and heat transfer. In the case of work transfer, we represent the differential work del W because it depends upon the path followed by the system. So that is why we are using this del. So del W equal to PdV. Whereas in the case of heat transfer, we say del Q equal to TdS, where T is the temperature and S is the entropy. Okay, so in the subsequent lectures, we will be studying about entropy. If you want to determine the displacement work, total work, then W1 to 2 is integral PdV between the states 1 to 2. If you want to determine the total heat transfer, Q1 to 2, Q refers to heat transfer, Q1 to 2 equal to integral 1 to 2 TdS between the states, state 1 to state 2, where P is an intensive property, where V is an extensive property. Here T is an intensive property, that means it does not depend upon the mass, whereas S is an extensive property which depends upon the mass. If you draw a PV diagram, then the area under the PV diagram represents the work transfer. And if you are going to draw a TS diagram, temperature entropy diagram, then the area under the curve in a temperature entropy diagram represents heat transfer. And we can say that displacement work, the reason for the displacement work is difference in pressure. Let us say you are going to have a cylinder piston arrangement. If the piston is going to move, this is possible only if the pressure inside the cylinder is going to be more than the atmospheric pressure. So wherever we have this difference in pressure, then this displacement work is going to be there. So difference in pressure is the cause and displacement work is the effect. In the case of heat transfer, difference in temperature is the cause and heat transfer is the effect. Coming to this heat transfer, basically we have two different types of heat transfer. One we call it as sensible heat transfer, other one we call it as latent heat transfer. Sensible heat transfer is nothing but the heat transfer during which we can see the change in temperature. If the heat is going to be added to the system, then we will see the increase in temperature of the system. If the heat is going to be rejected by the system, then we will see the fall in temperature of the system. Right? So during sensible heat transfer, we can see a variation of temperature or change in temperature is observed. But there will not be any change in phase. Whereas in the case of latent heat transfer, there is no change in temperature, but we will experience a change in state of the system. So there will not be any change in temperature, but phase change occurs. So if you want to calculate the sensible heat transfer, then Q is given as mc into delta T, where m is the mass of the substance and c is the specific heat capacity, and delta T is the difference in temperature. If you want to calculate the heat transfer during a latent heat transfer process, then Q is given as product of mass into latent heat per unit mass. So, and this latent heat, there are three different latent heats are available. One we call it as latent heat of fusion, and the other one we call it as latent heat of vaporization, and third one is the latent heat of sublimation. In the case of latent heat of fusion, this is a change of state from solid to liquid. When solid changes its phase to liquid, then that process we call it as melting. Right? So this is the heat transfer that is responsible for this melting process, that is change of state from solid to liquid, is what we call it as latent heat of fusion. The other way is also called as latent heat of fusion. If a system undergoes change of state from liquid to solid, right, this we call it as freezing or solidification. The whatever amount of heat that is required to convert a substance from solid state to liquid state, the same amount of heat will be rejected when the substance is going to undergo a change of state from liquid to solid. So liquid to solid, that change of state we call it as freezing or solidification. Similarly, coming to latent heat of vaporization, this is from liquid to vapor. So liquid to vapor we call it as vaporization, whereas vapor to liquid we call it as condensation. Right. So the amount of heat that is required to convert a substance in liquid state to the same substance in vapor state at the same pressure, whatever amount of heat that is required, the same amount of heat will be rejected when the substance or when the system is going to undergo a change of state from vapor to liquid. So the change of phase from liquid to vapor we call it as vaporization, whereas the vapor to liquid we call it as condensation. Now we have one more latent heat, which is nothing but latent heat of sublimation. So latent heat of sublimation is nothing but the change of state from solid to vapor directly, right, without any liquid phase or liquid state. So directly if the substance changes its phase from solid to vapor, we call it a sublimation. And similarly, if the other way, if it is going to undergo a change of state from vapor to solid, we call it as deposition or desublimation. Okay. So this is the process of sublimation. From solid, the substance becomes directly into vapor. Right? This we call it as sublimation. On the opposite process is what we call it as deposition or desublimation. In simple terms, I am representing all the phase transfers. Solid to liquid we call it as melting, and liquid to solid we call it as freezing or solidification. Similarly, from liquid to vapor, this we call it as vaporization, and vapor to liquid we call it as condensation. Directly, if there is phase change from solid to vapor, right? Change of state from solid to vapor we call it as sublimation. On the other hand, if it is change of state from vapor to solid, we call it as desublimation or deposition. Right? So there are basically 3 latent heat transfers involved. Coming to the last topic, that is zeroth law of thermodynamics. According to this law, assume that if you are going to have 2 systems, system A and system B, and these 2 systems are separately in thermal equilibrium with another system, system C, then we say that system A and B are in thermal equilibrium with each other. Now you consider this diagram or this object. This is object A, and we have one more object, object B. This object A is separately in thermal equilibrium with object C. Similarly, object B is also in thermal equilibrium with object C. Right? That means what? So this is in thermal equilibrium, and these 2 are in thermal equilibrium. When I say this is in thermal equilibrium, that means the temperature of A and temperature of C, object C, are same. Now assume that object B and C are in thermal equilibrium with each other. That means TB equal to TC. If that is the case, according to zeroth law of thermodynamics, then object A and B are in thermal equilibrium with each other. Now let us see an example how we are going to apply this law of thermodynamics. So now assume that I want to measure the temperature. For that you consider a pipeline. So this is a pipeline, right? So in this pipeline a fluid is going to flow, right? Assume that some hot fluid is going to flow. That fluid, let it be a steam. Now I want to measure the temperature of the hot fluid that is flowing through this pipeline. To measure that, there is a provision here. A pocket is available, and in that pocket I am going to place a thermometer. Thermometer is a device which is used to measure the temperature. So now the pipeline and steam are in thermal equilibrium with each other. Pipeline and steam are in thermal equilibrium with each other, and thermometer and the pipeline are in thermal equilibrium with each other. Correct? See, steam and pipeline are in thermal equilibrium with each other. Pipeline and thermometer are in thermal equilibrium with each other. If that is the case, whatever the temperature that is indicated by the thermometer will be the temperature of the steam or the hot fluid that is passing through the pipeline. So this is according to the zeroth law of thermodynamics. So this is the basis for measurement of temperature. Thank you for joining the lecture.